Hello there. This is Lab Report 2, The Motion of a Falling Object by me, Alexander Ardondo. So here's table of contents. We're going to have some formulas on this first slide coming up. We're going to have basically like free body diagrams that break down the analysis and analyze this motion. We're going to have a few graphs, one from Tracker, and then two from Python, one with and without drag, and then going to answer some of the what-if questions about terminal velocity. So here are the formulas used. Newton's second law is obviously the first one that we have on here, just talking about how to find F net and how it's related to momentum. And then our prediction formulas that we have basically is derived from Newton's second law. Forces, this one's actually relevant to our lab. So for the drag force, we need it's equal to the drag coefficient, which is b times the magnitude of the velocity squared, and then v hat, which is the direction that's going in. So we'll see in this that the drag force will actually be positive while the gravitational force is negative, just because it's going to be resisting the ball going upwards. So you're going to get a lower F net when you have drag opposed to when you don't have drag. And so the other forces we have is just gravity. Without drag, it's just gravity, and then with drag, we have gravity plus the drag. All right, so now we're just kind of getting into the lab and what we've done. So here's how you assume the objects or the forces on an object. So these two arrows kind of just display like what's going on. The white one being the gravitational force, and the yellow one being the drag force. So with drag, eventually the drag force will begin to cancel out the gravitational force, and this is when we reach into terminal velocity. And without drag, it's just the gravitational force acting on this object. So we'll see that when we drop our object and analyze it with Tracker, that there will be drag on that object, opposed to when we put it into the code, we'll get a little bit different numbers due to the fact that we're not assuming drag in that assumption. So here's actually the Tracker video. Here's it following a parabolic function. And then here it is bigger in Excel. And then so when we look at this in a time graph, we can see there's an acceleration because each one of these dots are getting further and further apart from each other until it gets to a certain point where drag is acting on it in such a way that it's starting to slow the acceleration. But we'll get into that later. We're going to end this lab. But yeah, similar to the first lab, when you try to calculate line of best fit, it's not going to be exactly one due to the fact that there are external forces. In the last lab, it was friction. In this lab, we're looking at drag. But it's just a couple of things that will throw your line of best fit out of whack. And so basically in this lab, our system surroundings are defined as this. We have our system, which is the ball that's dropped. And we have our surroundings, which is just Earth and the gravitational force that acts on the ball. And when we do account for drag, we actually have to figure out that air is another part of the surroundings because it slows the ball when it's in free fall. And then here's our Python code without drag. I just took the standard code, and here's the edits I made. I changed the mass from whatever was given to 0.145 kilograms, which was the weight of the ball. The position and velocity vectors are both the zero vectors because I'm assuming that when I have it I'm defining when I drop it, that's the zero position, and then when it starts to fall, it's starting from a zero. It's starting with zero speed, and then the time interval I chose was 0.667 seconds because that's how long our video on Tracker was. And then for finding F net, we just kind of used gravity and j hat, which is just the vector in the y position, and then our F net is just gravity in this case. And then for our prediction formulas, it's pretty much exactly what we did in the last lab. Just the velocity is equal to the final velocity is equal to the initial velocity plus F net divided by the mass times delta t, which is just exactly what we have in our code, just written in the Python syntax. And then the update position is the same as what I just explained for the velocity prediction. And however, this is very different. The code with drag, it's pretty similar to what we had before. However, there are just a few tweaks. First off is we have a coefficient of drag, which is our b in this case, which is found to be 0.02403884. I know, very precise. But this is how I found it. I just kind of went and I used the data from Tracker and that final position, and then I ran the code with drag and kept on updating and changing the drag coefficient until I found that the final positions were the same for both cases in Tracker and when I ran it with this code. And then yeah, to calculate the F net in this case, we had to incorporate the drag, the force from drag. So you have to multiply the drag coefficient times the magnitude of the velocity squared times j hat, which in this case, like I said, is just the y portion of the vector. And yeah, so here are the two graphs that we actually get from this. On the left, the object falling without drag, you'll see it falls to a position of 2.185 meters, and the line of best fit is equal to 1, meaning that it's a very smooth line. There's no confining factors on it, such as outside forces of gravity. And then on the right, we'll have the object falling with drag, and you'll see it actually ends up falling a lot less. It falls less, and the location it ends at is 1.964 meters, and the slope is not uniform due to the fact that it has other forces acting on it other than just gravity. All right, now what does this all mean? So after putting all three of these into a single chart in Excel, we can see that our model with drag ends up, our model without drag in Python ends up falling a total distance of 2.185 meters, whereas the models with drag, that being our Tracker and our Python with drag, they only fall 1.964 meters. So our assumption, and you can see that the gray line, our Python with drag, and our Tracker data are not exactly the same. And this is because the method that I chose to find our drag coefficient is not entirely true. It does give a good baseline and assumption, kind of like how when we calculate the final velocity or the average velocity, we just take it to be the final velocity in some cases. This is the same reasoning that I chose to have this be our Python with drag line. But it's not entirely true. It's a bit more shallow than our Tracker data, and that's just because there's external forces acting on the Tracker, on the object in real life that we couldn't account for in our code. But after that, the two graphs that kind of do predict terminal velocity is both our Tracker data and our Python that has drag included. And kind of getting into what terminal velocity is, it just means that the net force is zero, so that the magnitude of the drag force is equal to the gravitational force. So like I showed in our free body diagram, those arrows will actually have the same magnitude, and it will cause it to have no more acceleration, but it will still be traveling at a certain velocity. That's why it's terminal velocity. So it's just not going to be continuing to speed up. It'll just reach this terminal velocity. It'll continue at this velocity, but it won't be accelerating anymore. And so just kind of getting into like what if. So to see what terminal velocity like really means in this case, we'll have to have an increased time interval to see the how drag affects an object. And in the data that we had, previously, it didn't really display terminal velocity because there was not enough, it wasn't a big enough sample size to really see the effects of drag canceling out gravitational force. So seeing this, we have the drag or the terminal velocity of this object when running it in our Python code is about -7.7 meters per second. So that's how fast it's going. And then comparing the data, the orange line is with an initial velocity and the blue line is without initial velocity. We'll see that both of them actually reach the same terminal velocity. So it doesn't really matter if there is an initial velocity. The only thing that matters if there is initial velocity is how fast it actually reaches the terminal velocity. So the orange line will be approaching terminal velocity quicker than the blue line. However, you can't exceed this terminal velocity because that's how fast an object can fall in that period. And that's about it.